You may not think of mathematics as a debate, but it turns out that the puzzle of parallelism created a lot of intrigue and drama for mathematicians starting way back in 300 BC when Euclid published his Elements, the text of which served as the geometry textbook for the next 2100 years. To understand the puzzle, you need to know that there are two types of mathematical knowledge. We have facts that we assume to be true. They're called axioms. We also have facts that we prove to be true, and those are called theorems. But we have to assume in mathematics that certain foundational things are true. So the debate, the puzzle was whether or not Euclid's parallel postulate, his fifth postulate, was it a theorem or was it an axiom? Could it be proven from the first four, which would make it a theorem, or did it need to be an axiom, something that we assume to be true? And to kind of give you the scope and majesty of this quest, here is a father-son duo that both looked at the puzzle of parallelism. The father right around 1800 and the son solved it in 1832. And, or in the late 1820s, early 1830s. And look, the dad saying, "Hey, I've been to Mordor, and this quest has extinguished all light and joy in my life. Don't do it, son. Don't do it." And years later, after the son has disobeyed his father, as sons will, he writes back to his father, and after he solved the problem, this puzzle that has tortured mathematicians apparently for 2,000 years, he feels godlike, as though he's created a strange new geometric universe. And the godfather of mathematics, Carl Friedrich Gauss himself, even worked on this problem and independently of Boole solved the problem. So these are great mathematicians over the years who've contributed to our understanding on the puzzle of parallelism. So I'm trying to give you an idea of what the problem is. So there are three basic types of geometry that could start off like Euclidean geometry. Now, the Euclid's first four axioms, the assumptions we make, get rid of all elliptical and spherical geometries. And they knew that. They had studied, the Greeks studied spherical geometry, knew it wasn't possible. What they didn't realize was this idea of hyperbolic geometries were all possible if you only assumed Euclid's first four. So what Euclid's fifth does is Euclid's fifth focuses us on a particular geometry and gets rid of the possibility of a hyperbolic geometry. And to understand a little bit about what's going on here, let's talk about Playfair's postulate. So John Playfair, who was in the late 1700s, he restated Euclid's fifth postulate, and this is the parallel postulate most people use right now. So Playfair's idea was, suppose we have a line L and a point P that's not on it. Then there is at least one line parallel to L that goes through P. Now, for Euclidean geometry, we think of it as there is exactly one line, and that's true. There's exactly one line through P that's parallel to L. But what turns out to be true is that hyperbolic geometry is possible as well, where there's some curvature to the lines. And we have line L and point P. The problem with hyperbolic geometry, it turns out that there are infinitely many lines through the point P that can be parallel to L. So that was a big problem. Now, Euclid's first four postulates do rule out elliptic geometry. Why? Well, because there were no parallel lines at all. And in elliptic geometry, the lines, there's curvature to the lines, but they're curving in on each other. And so there are zero parallel lines. Okay, and then to further understand this, let's just note there's this riddle, and I'll just tell it to you. Suppose you're at the North Pole, right? And you're at the North Pole and you start walking south and you walk 1 mile south and then you turn right 90 degrees. Okay, so now you're walking west, you walk 1 mile, you turn 90 degrees and you walk due north. It turns out that you'll be right back where you started, which is the North Pole, right? And the idea of the riddle is if you do this and you see a man with a long white beard, where are you? Well, it's Santa Claus and you're at the North Pole. But this is just illustrating what happens in these elliptical and spherical geometries. We sort of have these fat triangles, you might want to think of them that way, where the angle sums are greater than 180 degrees. You see, we have two right angles plus whatever angle measure is in this one. So in a spherical geometry, we have angle measure that's greater than 180 degrees. And then with these triangles where things curve in, right? I can think of a hyperbolic triangle here, right? And they're kind of thin triangles where their angle sum is less than 180 degrees. So we definitely need a parallel postulate to untangle this whole mess. And that's looking back now, we can understand why they were confused. So with just a neutral geometry where we assume no parallel postulate, we just assume the first four Euclidean postulates, the only thing we can prove is that the angle sum of a triangle is less than or equal to 180. Now, if we're in an Euclidean geometry, if we know that all angle sums are 180 degrees. But we're not. We're going to try to prove that what we can without assuming a parallel postulate. The proof I'm going to do is very Greek. The Greeks developed what they called the method of exhaustion, and they had the same intuitive idea of limits and infinity that we have, but they didn't have the mathematical architecture to do the kind of convergence proofs and proofs using ideas of infinity that we can do in modern times. But they did understand the idea of exhaustion, and the way they thought of it was sort of subtracting things out until there was nothing left. For example, suppose we're standing 10 feet apart, and then I move half the distance towards you. Well, now we're 5 feet apart. We've subtracted out 5 feet out of that distance. And then I move halfway towards you again, and now we've subtracted another 2.5 feet, and I move halfway towards you again, and now we're 1.25 feet apart. And they would think of this continued subtraction as meaning that over time, as you think of forever going out to infinity, we will eventually be standing on top of each other, right? We'll be at the same place. We will have exhausted all of the distance that's between us. And the proof we're going to use is very similar to that. Now we need a couple lemmas. Lemmas are sort of baby proofs. They're statements we'd like to just use in our proof, so the proof will be more understandable. So we're going to break these out and prove them initially, and then when we do the big proof, it'll be a lot easier to understand. So I've got a link there for you. And here's the lemma. Right, we assume that we have an arbitrary triangle ABC, and what we're going to do is we're going to extend the line so we have these exterior angles. Why? Because we have a theorem that says the measure of an exterior angle is greater than or equal to the measure of either remote interior angle. Here we're just labeling the angle near A as alpha, the angle near B as beta, and the angle near C as gamma. And then we're applying the theorem I just mentioned to get three inequalities. The first one is that alpha is less than, the measure of angle alpha is less than BCD. Well, we're talking about this exterior angle here, and inequalities 1 and 2 just say that that angle measure, that exterior angle measure, has to be greater than equal alpha or beta. And the other one, or the other exterior angle over here by A, is going to be greater than or equal to the measure of gamma, and that's the third inequality that we make. The mathematical property we're using is just that I can add the same number, the same real number, to both sides of an equation. And the definition of linear pair, which just means that I have a pair of angles that end up forming a line, and that means that their angle sum is 180 degrees. We're not saying the angle sum of the triangle is 180 degrees, we're saying that the angle sum of a linear pair is 180 degrees, and there's a difference. So, the next thing we're going to do is we're going to add gamma to both sides of equation 1. And look what happens. So gamma is also equal to the measure of BCA which is a linear pair with this exterior angle. That way we know that their angle sum is 180 degrees. And therefore we know that if I take the measure of angle alpha and angle gamma and add them together, I'll always get a number that's less than or equal to 180 degrees. And I do the exact same equation I do the exact same thing for equation 2 and the exact same thing for equation 3, although for equation 3 I'm using a slightly different substitution because here I need to use the linear pair on the other side of the triangle, the one that's remote to gamma. Okay, so now we know that since the angle we chose at the beginning was arbitrary, since the triangle we chose at the beginning was arbitrary, this is true for every possible triangle in a neutral geometry. So this is the fact that mathematicians kept bumping up against. They could always prove that the angle sum of a triangle was less than or equal to 180 degrees, or that the angle sum of a quadrilateral was less than or equal to 360. They were having trouble proving that equality. They couldn't get there without assuming a parallel postulate. So here's where the Greek idea of method of exhaustion comes in. So what we're going to do is we're going to use Lemma 2 to create successive triangles, and they're going to have a very interesting property, right? We're going to create a new triangle based on an arbitrary triangle we start with, and we're going to make sure that the triangle's angle sums are absolutely equal. What I'm going to do is I'm going to create a triangle, the new triangle, so that this angle at A prime is less than or equal to half of whatever the angle measure was here in the original triangle at vertex A. And this is going to give us that triangle AMB is congruent to triangle DMC. Now we've almost got it. Look at this step. So as I add in the angles, remember I have triangle congruence. So the green triangles, the green angles are equal to each other in measure, and the blue angles are equal to each other in measure. Okay? So if you look at the fact, right, we have these triangles are congruent, right, by SAS, sorry about the mess. So I know that corresponding parts of congruent triangles are congruent. So I know that angle theta here is congruent to angle beta. Theta and beta are congruent. And I know that angle B here and the green part of this angle here are also congruent. But notice what's true. If I just focus on the triangle ABC, what angles are left over if I don't have the green angle measure, right? I've got the blues. I've got this piece of angle A over here, and I've got this whole angle, this angle in blue. And so I take the first green one, the second green one, and the two blues, and that's the angle sum of the first triangle. Well, look at the second triangle. So now I have this longer side with a green angle, the first green angle, the second green angle, and the two blue angles. Those are, if I add all those up, I have an angle sum of the triangle, which is exactly the same as the other. So we do have the fact that these two triangles that we've created, triangle ABC and triangle ADC, have the exact same angle measure. So now we have to relabel this triangle, right? C is going to be C. The question is whether or not I put A prime down here, right? Or whether I put it up here. So the question is, right, do I relabel A as A prime and let D be the new B prime, let C be C prime? Or do I do the opposite where A prime goes up here? We have proofs of both of these lemmas. So let's start the proof of the Saccheri-Legendre theorem. And what we're going to do is we're going to use lemma 2 to create a contradiction with lemma 1. Let me show you how that goes. So the first thing we're going to do is assume that there's some arbitrary triangle T1, and whatever its angle sum is, let's just make sure that it's 180 degrees, greater than 180 degrees, because the whole point is we're going to contradict that. It's impossible and we're going to prove that it's impossible. And all we're doing here is a little mathematical trick where we say, hey, if it's greater than 180 degrees, then there's some real number over here so that I can say its angle sum is equal to 180 degrees plus this real number. And the key thing is that the real number of degrees has to be strictly greater than 0. That'll be important. Again, if the angle sum is bigger than 180, we can do this. Now I'm going to be using the method of exhaustion. And so we're just saying here that there are 3 angles. The one we're focused on is theta. That's the one that's going to be our A that changes in size. And it's got 2 other angles. And if we apply lemma 2, we know that there's some additional triangle, T2, that has the exact same angle sum as T1, but its new theta is less than or equal to half of the old theta. And if we repeat this process, the idea is that we can keep going and going and going using the method of exhaustion until we get to some point out in the sequence where the measure of angle theta sub n is strictly less than whatever the delta is. So we're reusing lemma 1 over and over and over so that we have a triangle T3. Its angle sum is the same as T2 and therefore as T1. But now we know that the measure of the angle theta 3 is less than half of theta 2, which was less than or equal to half of the measure of angle theta 1, right? Sorry, oops, I forgot my half in here, less than half, right? So what we know is that theta 3 is less than 1/4 of theta 1. And then we create T4, it has the same angle sum as T1, 2, and 3, and then its angle, the measure of angle theta is less than half of the measure of angle, the measure of angle theta 4 is less than half the measure of angle theta sub 3. So now we have the measure of angle theta sub 4 is less than 1/8 of the original theta 1 angle. And we just keep going and going and going. And we've done this over and over and over. And every time the measure of the new angle is less than or equal to half of the old angle. And I created this illustration to show what's going on. The first angle is here, and we're looking at this angle A or theta, whichever you prefer to call it. We called it A when we were proving the lemma. And then I create T2, and this angle is smaller. And then I create T3, and this angle keeps getting smaller. And the idea is that this angle theta n, it's going to get smaller and smaller and smaller, and eventually, in the limit, it goes to 0. This is the method of exhaustion, where eventually we end up with a theta n, and we know that we've done this n minus 1 times, actually. It's not quite n times, but we know that this theta, the measure of angle theta sub n, is less than 1 over 2 to the n times the original measure of the angle theta 1. The final part of the theorem is a little bit tedious mathematically, but the key idea is right here. We're just saying, hey, I can keep applying lemma 2 over and over and over and over and over and get theta sub n as small as I want to. I can get it as close to 0 as I want to. So the math details go like this, right? I choose, by the Archimedean principle, a natural number so that I know that that natural number is larger than whatever the measure of angle theta 1 is divided by delta. And I'll show you why we're doing that. We have some math that demonstrates that when I do this, I'll get my original angle divided by 2 to the n less than delta degrees. Okay, how does that work? Well, we know this is what we assume to be true, that n is this big. And what's the Archimedean principle? The Archimedean principle for mathematics is that for any real number, we can choose a natural number, an integer, that's bigger. And then we just take the reciprocals and notice that the inequality flips, right? Because we're taking the reciprocals. And this is the fact that we put in here. If 2 to the n is greater than n, then 1 over 2 to the n is less than 1 over n. But this, 1 over 2 to the n, is going back to what we know from before. So now we're done. Remember where we began. We started with a triangle T1 and we chose this delta so that when I added the measures of the three angles, I would get 180 degrees plus this real number delta degrees. Okay. Well, what we've shown is that we can replace this with theta sub n and know that the theta sub n is smaller than the delta degrees, right? So what does that mean? That means that if this angle measure is less than the delta degrees, then when I add these two guys together, their angle sum is going to be more than 180. Well, that's our contradiction. That contradicts lemma 1, which says that the angle sum of any two angles in a triangle has to be less than or equal to 180. And remembering our original assumption that T1 was arbitrary and had an angle sum strictly greater than 180 degrees, that leads to a contradiction. That simply cannot be true, which is why that proves that for this T1, our angle sum must be less than 180 degrees. And therefore, because the triangle T1 that we chose is absolutely arbitrary, the same proof will hold for any arbitrary triangle in the entire neutral geometry, and therefore holds for all of them. To really understand why this is important, let's think about the situation where we try to prove this in Euclidean geometry. So suppose we have some triangle, and the way that we prove that the angle sum is equal to 180 is we extend the base like we did for our lemma, right? And we notice that if we draw a line through P that's parallel to this base, then the alternate interior angles theorem gives me congruence of these two angles, gives me congruence for these two, and then this angle is congruent to itself. So what we know then is that the angle sum of the angles in a triangle add up to a straight line. Linear pair or linear triple has a 180-degree angle measure. But it turns out that this theorem, that a triangle has 180 degrees, is exactly the same thing as the alternate interior angles theorem being true, specifically the converse of the alternate interior angle theorem, which says that if two lines are cut by a transversal, then alternate interior angles are congruent, which is also equivalent to the parallel postulate. So as they were proving the Saccheri-Legendre theorem, what mathematicians were doing is they were isolating just exactly what was going wrong and why it was that the alternate interior angle theorem was equivalent to Euclid's parallel postulate. And so this is the story of the conclusion of how a 2100-year-old puzzle was solved.